Our atmosphere is composed of around 78% nitrogen, 21% oxygen, and a few trace gases. Oxygen and nitrogen have very different properties, but in a mixture they behave as a single entity. In this chapter, we'll explore the behavior of gases. There are 12 elements on the periodic table that exist as gases under ordinary conditions. Hydrogen, nitrogen, oxygen, fluorine, chlorine, all of which are diatomic, as well as helium, neon, argon, krypton, and xenon, and radon, which are our noble gases. And while these gases are diatomic, the noble gases are monoatomic. There are also a number of molecular compounds that are also gases, all made of nonmetals. They all have pretty simple molecular formulas, which means they're going to have fairly low molar masses. Gases behave differently than both solids and liquids. Some properties of gases include they expand to fit their container, they're highly compressible, they form homogeneous mixtures with each other, and the gas molecules are not really attracted to each other, so they stay pretty far apart, which is why we can compress them. Pressure is a force that acts on an area, and it's measured by using a barometer. The mercury barometer was invented by Evangelista Torricelli. Here's how it works. A glass tube is evacuated, all of the air is removed from it, and it's filled with mercury. And then it's turned upside down and placed in a shallow dish, which also contains mercury. As the gases that make up our atmosphere exert a pressure on the mercury that's in that dish, it'll cause the column of mercury to rise. Or if atmospheric pressure decreases, then the mercury in that column will go down. And so we would read the height of that mercury column in terms of inches of mercury or centimeters of mercury or even millimeters of mercury. The SI unit for pressure is the Pascal. Remember that force is measured in newtons and area is measured in meters squared. And so the Pascal is newtons per meter squared. Standard atmospheric pressure is the typical atmospheric pressure at sea level and will support a column of mercury that is 760 millimeters high. So standard atmospheric pressure then is 760 millimeters of mercury, or 760 torr, which is short for Torricelli. So standard pressure is 760 torr, or millimeters of mercury, and that is equivalent to 101.3 kilopascals, which is also equivalent to 1 atmosphere of pressure, all different units that reflect the same value. We said that gases are highly compressible. This means that we can take gas molecules and by applying pressure to them, we can push them really close together so that they occupy a smaller volume. Gases will also expand to fill the volume of their container. Weather balloons expand as they rise in the atmosphere because the pressure decreases as we go up into the atmosphere, allowing the volume of the molecules inside the balloon to expand. This relationship is explained by Robert Boyle in the late 1600s. Boyle's law states that A fixed quantity of gas at a constant temperature is inversely proportional to the pressure. So, as we increase pressure, volume will decrease, and vice versa. Mathematically, we could also express this as such. To plot volume versus pressure, we would get a curve that looks like this. However, if we plot volume versus the inverse of the pressure, then we would see a linear relationship. Boyle's law is put into practice every time we take a breath. When we inhale, the diaphragm moves down, and our thoracic and abdominal muscles expand. And that changes the volume of the lungs. So as the lungs expand and the volume of the lungs gets bigger, the gas pressure in the lungs decreases. And so air will move into the lungs until the pressure on the inside of the lungs is equal to the pressure on the outside of the lungs, which is atmospheric pressure. And then our muscles contract, the diaphragm goes back up, and the pressure increases in the lungs so that gas is exhaled. Sometime in the early 1800s, Jacques Charles also looked at the relationship between variables and the behavior of gases. He looked at temperature and volume while holding pressure constant. And what he found was that there's a direct relationship between volume and temperature. So as he increased the temperature of the gases, the molecules moved faster, gaining kinetic energy, and increased in the collisions that they had, and therefore expanded, taking up more space or increasing in volume. And so if you take a look at this graph and consider it in the opposite direction, if we were to cool these gases and we were able to make them really, really, really cold, and if they didn't solidify, which they would at really cold temperatures, would it be possible to reach a temperature that was so cold that the substance occupied no volume whatsoever? Well, if we take that data from our volume temperature relationship that we have graphed here, and we extrapolate it a little bit further, we would see that the temperature at negative 273 degrees Celsius is the point at which volume would be equal to 0. And so, in 1848, Lord Kelvin proposed an absolute temperature scale, which is based on the Celsius scale, at which negative 273 degrees Celsius corresponds to 0 Kelvin, or absolute zero. And that's the basis of Charles' law, which states that the volume of a fixed amount of gas is directly proportional to its absolute temperature. And mathematically, we would express that as volume divided by temperature is equal to a constant, or the volume of a gas is equal to a constant times temperature. One last relationship we'll look at is that of a volume and quantity of a gas. If Louis Gay-Lussac was a hot air balloonist, he was also a scientist. He's credited with explaining the law of combining volumes, which states at a given temperature and pressure, volumes of gases that react with one another are in the ratio of small whole numbers. Since 2 hydrogens and 1 oxygen make 1 water molecule, if we have 2 volumes of hydrogen and we combine that with 1 volume of oxygen, we'll end up with 2 volumes of water molecules, which then caused Avogadro to propose that equal volumes of gases at the same temperature and pressure must contain the same number of molecules. And so 22.4 liters of a gas at STP, or standard temperature and pressure, contains 6.02 times 10 to the 23rd gas molecules, which also happens to be equivalent to its atomic mass in grams, giving rise to Avogadro's law, which states that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of gas, or the volume of a gas is equal to a constant times N, or number of moles of gas. So doubling the number of moles of a gas then would double its volume, as long as temperature and pressure are unchanged. So far, we've looked at the effects of pressure, volume, temperature, and number of moles of gases. In each instance, we've looked at two variables while the other two were kept constant. In the next section, we'll take a look at the combined effects of all of these variables on the behavior of gases.